So this is the last of the big three. So we've had metallic bonding and ionic bonding, and now we've got covalent bonding, all with electrostatic, so all positives attracted to negative. And so this one is electrostatic attraction between a shared pair of electrons and positively charged nuclei. So that's the bonding pair, the one that has both nuclei attracted to it, and the electrons that are on the outside that don't have that are the non-bonding pairs of electrons. And so what happens is there's a happy medium between the two. So the two nuclei, they're attracted to the electrons and they're drawn into each other. It's nice and close. What happens is the two positives then start repelling each other. So that's this case here. So there's a limit to how close they can get to each other because the two positive nuclei start repelling. And as long as that's not the case, they just keep closer and closer and closer. And so the happy medium's around here. So that's the amount of energy that gets released when the bond forms. And it's also the amount of energy you need to break the bond. And that will determine the bond length as well. So moving on here. So covalent compounds, there's two types. There's ones where they're all joined up in a lattice. And so here you've got carbons all joined to each other. This one you've got, for every silicon, there's two oxygens. If you draw that out, that one actually doesn't work. So I need to draw it from there and from there and from there. So a little bit awkward in how that's done, but for every silicon, there's two oxygens. So that's the empirical formula, the lowest whole number ratio. This one's a litlittle bit unique because it's actually an element, not a compound, but it's still all the elements are joined up in covalent bonds in one big lattice. And so those things are quite different, obviously, from because they have high melting boiling points from these simple covalent molecules. And that one is actually compound, and that one's a molecule, covalent compounds, all right, because that is just the entire covalent compound. And then they're only attracted to each other through weak intermolecular forces, which we'll cover soon, IMFs. Now, we've had these magic numbers before, so here they are again. So ionic compounds are greater than 1.8, and the strongest one you can get is if you go right to the top right-hand corner is fluorine, and right to the bottom left-hand corner is cesium. And even then, how do you say that it's completely over this side? Is it like 100% on this axis here? So almost nothing is completely ionic, although you can sort of have completely covalent because you can have the diatomic molecules. And so they're both exactly the same. And so you can theoretically kind of say that they are exactly in the middle. So as you can see, pretty much everything is somewhere on the spectrum here. So they're either really close to being ionic and considered ionic, because it's anything greater than 1.8 we're going to consider ionic. Anything less with an electronegativity difference less than 0.4 we're considering non-polar covalent, and everything else in between is some sort of polar covalent bond. So one side slightly positive, one side is slightly neg. Now, naming covalent compounds is the easiest as long as you've learnt monos 1, dis 2, tris 3, tetras 4, pentas 5, hexas 6, heptas 7. You're not really going to get up this high. And so that's how you name and write them. So you just don't say mono at the very start. And as I've said before, the anions for ionic and covalent bonds are always given this "ide." So if you have carbon and oxygen over here, you don't say monocarbon, you do say monooxygen, and you convert the oxygen to an "ide," so it's carbon monoxide. So that is fairly simple. Not I've tested too often for some reason either. And so we're going to move on to how to write them. This is quite important as the first step to learn how the correct structure is. And so the first thing you're going to do is, first of all, just set the ground rules. So we're going to see all of the electrons, whether they're bonding or non-bonding, and they're in pairs because each orbital can hold 2 electrons. And we're only going to do the octet rule. We are going to introduce exceptions to that don't make it to 8. And just be aware, the height levels will know this quite well, that once you get too big, you can easily extend the octet, and that's around period 3, because you're going to see it all the time, but you're not going to be tested on that if you're standard level. And so how do you draw them? You put the one that's not seen very often. It's just like 1, so it's like SO4. So if you put the S in the middle and the oxygen's all on the outside. If it's not so clear, you'd put the most electronegative one on the inside. And so that's how you start it. This one's just oxygen, so they're even. So write out the elements, look at the periodic table, read across, and you'll see there's 6 electrons in the principal energy level of the valence electron shell. So do that first. They automatically get one bond because by definition they're a compound. So draw one in and then count to see if it hits the 8. If it hits the 8, you're done. It's one bond each. If it's not, you've got to do a second and third. So if I count these out, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. No. So they've got to be 8. So try drawing another bond in there. And so when you draw another bond in there, it's 1, 2, 3, 4, 5, 6, 7, 8, and 5, 6, 7, 8. And so it must be a double bond. Now, if it's not the case, usually take the one that has the most number of electrons and give it something called a coordinate covalent bond. Now, the coordinate covalent bond, these don't have their names on them. They don't tell you, oh, I was the electron that was, put into this coordinate covalent bond. You can't tell the difference between coordination covalent bonds and covalent bonds. But it's nice to draw it in there to show how it was formed, even though there's no difference between the coordination bond and a normal covalent bond. And so if nothing works, then try this and that'll usually work. If that doesn't work, you've got a radical, which they're not going to do to you. It's been incorrectly drawn or something, which is usually what happens if you find out you can't balance something. It's actually you've written the chemicals out wrong. So if you put the 2 over here, then you've got 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. And then it does work for carbon monoxide. Okay, so once you've done that, you just need to clean it up. Now, the clearest way to do it is to put the X's for one of them and the dots for the other. I prefer this because it's quicker, and that's the proper way to write a dative or a coordination bond. And so that each line represents 2 dots. So that's my preferred way. So do your working first, so you make sure you get it correct, and then do your cleanup afterwards. If it is a ion, make sure you do square brackets and show the charge on the outside, and make sure you've added 2 electrons into the system. If it's a plus, make sure you've removed one of the electrons out of the system when you're working out what the overall charge, what the bonding is. Now here are the 2 exceptions. Boron is slightly out and beryllium is even closer. So if you look at hydrogen, helium, and lithium, they all go just to that first shell, so they're very small. Beryllium is the next in line, and because its atomic size is so small, there's steric hindrance, and they can't fit that much around it. So it can only actually fit 2 in there. And same with boron up here. It's 1 proton larger, so slightly larger nuclei, and it can manage to fit 3. You can't sterically fit, because it's so tiny, another chlorine to come in there. And so that's all it can fit. So that's breaking the octet rule. And the last thing we're going to cover for the time being, so we're going to have quite a few, we're just going to concentrate on covalent substances really for the rest of this unit, is bond length, bond number, and bond strength. So if you have like lots of single bonds and you're comparing them all, the one that's shorter will also be stronger. But if we're going across here, you'll also note that if you add a second or third bond, it's actually getting shorter and it's also getting stronger. The only catch to this is because it's so negative, it's going to attract positive species, and they're called electrophiles. And so it's actually going to react, and so the bond's going to get broken because it's reactive, because there's a concentration of electrons. The other thing that's sort of they don't really talk about is per capita that's actually weaker. So if you divide that by 2 and divide that by 3, so those bonds are not as strong as 347 each. So they don't contribute, they're actually making it weaker. And you'd expect so, because throwing so many electrons in there is going to cause repulsion. So you expect it to actually be weaker. So that's ironic. So just be aware of those ideas